Hi folks. Today we're going to talk about similar solids and what happens to a three-dimensional object when we grow it or shrink it. The first thing I want to talk about is how do we express this? What does scale factor look like when we're talking about dimensional or three-dimensional objects? So the first thing we're going to start with is we're going to say that there is a scale factor, and we're going to call it A over B. That could be 1/2. It could be 4/1. So we're going to let AB be the scale factor between two objects. Given that, if I look at the perimeter of the first one and compare it to the perimeter of the second one, then that's going to have a ratio of A to B. So if the first one is smaller by half, then the perimeter of the first one is going to be half of the perimeter of the second one. Something similar happens for area. The area of the first one can be compared to the area of the second one. I'm going to stick with the idea that the first one is half the size of the second one. In this case, then my area is actually going to grow in two dimensions. It grows both in the length and the width. So we would expect the area of the second shape to be smaller or larger by the square of that scale factor. And then volume is similar. The volume of the first one can be compared to the volume of the second one in such a way that because volume is three-dimensional, the ratio of the change will also be in the three dimensions. And so my ratio would be A to the third power and B to the third power. That can be expressed in the similar solids theorem, which I'm going to let you read. But I think all of this makes a lot more sense if we actually look at concrete examples. So let's do that now. Let's look at example 1. In example 1, I am showing you a solid A, it's nicely labeled, and it's similar to solid B. If you remember, similar means it has the same shape and just different scale factor. So my solid is not shown, and you could draw it in if you wanted to, and it's given a scale factor of A to B, and they're asking me to find the surface area and the volume of solid B. The first thing I need to note is what my scale factor is. My scale factor is 1 to 2. This doesn't mean it's going to be half, the new figure is half the size of the old one. This means the first one is one size and the second one is twice that size. So if I were to write out what does that mean, I would write it as something, my scale factor is original shape over my new shape. And in this case, the new shape is twice the size of my original. So it's a little It's a little misleading because it almost makes it look like the new shape is going to be half the size, but it's actually the reverse. Okay, so that means if the radius of my original shape was 5, the radius of my new shape will be 10. Just to give you a little concrete example there. We see from up above in our theorem that our scale factor is going to change by the area of the first one squared and the area of the second one squared. In this case, the scale factor will square. So my scale factor, the original one, the area is obviously going to stay the same. But instead of being twice as large, my new shape is actually going to be 4 times the original size. Same thing happens with my scale factor when I look at volume. The volume of the first one is going to stay the same, but my volume of the second one, actually I should put an O here for original and new maybe instead of 1. So I'm going to change that to an O and this to a new, and that's going to change by my units cubed. The volume of my original, or my scale factor originally, the new figure is twice the size, but because I'm growing length and width and height now, then I'm going to grow by a factor of 8. My volume will be 8 times the original volume of my figure. So what does that look like? How do I answer this question? What I'm going to do is I'm going to use my surface area. If my original surface area, which I am going to draw in with blue, if my original surface area was 42 pi, then I can compare that to my new surface area, which I actually don't know. So I'm going to give it an X, because in math, when we don't know something, we give it an X, but I know that that has to be in a ratio of 1 to 4. I know that this new shape is going to have 4 times the area of the original shape. So if I use cross multiplication, or if I, however you choose to solve this, what I end up with is a new area that is equal to, as we described, 4 times my original area, which in this particular case is going to be 168 pi feet squared. So that's how we can use our scale factor to help us find what happens to the dimensions when a shape grows or shrinks. I can do the same thing with my volume. If my original volume was 36 pi, then I can express the original volume, and I can compare that to the new volume. Let's use a different color just for grins and giggles. My new volume, I don't know, but I do know that it has to be in a ratio of the original to the new figure, and that will grow by my scale factor cubed. So the new figure is going to have 8 times the volume of the original figure. And again, when I use cross multiplication or whatever the trick is that you use to solve this, I come up with a new volume. It's 288 pi feet cubed. So without knowing the exact dimensions of an object, I can predict what's going to happen to its area and volume based on a scale factor and some dimensions of the original figure. Let's look at another example. Example 2 is actually very similar to example 1, so I skipped that. And instead, I'm going to look at example 3. In example 3, I'm told that A is similar to B, but I notice in this case, figure B is smaller. So that tells me my scale factor is going to look a little different. I'm asked to find the perimeter area and volume of scale factors of the two shapes. So I'm given the surface area of both of them, and I'm asked to, from that, deduce what the scale factor is. So I'm going to first think about what scale factor means when I'm talking about surface area. To do that, I need to remember that my surface area is going to be my original shape compared to my new shape, and that my surface area grows by the scale factor squared. So the numbers I'm looking at have already had that squaring applied to them. All right, let's fill in what we know. The original shape was 208. The new shape is 52. And if I simplify this fraction, I end up with a squared surface area scale factor. This isn't surface area, this is my scale factor. My scale factor of my area is 4 to 1, which means my new shape, or my original shape, was 4 times the size of the new one. The new shape is 1/4 the original. Okay, that's not my actual scale factor. This is my scale factor when it's been squared. And that's important to note, because now to find my actual scale factor, that is going to be equal to my area scale factor, which was squared, and I need to take the square root of it, right? To undo this squaring operation, to undo scale factor squared, I take the square root. I can apply that here. I can take the square root of 4 over 1. That's really the square root of 4 over the square root of 1, if we remember our radical operations. And both these are perfect squares, so I end up with a scale factor of 2 to 1, which means that while the volume of this one, the surface area of this one, is 4 times the surface area of B, when in talking about actual dimensions, like its length or its width or its height, this shape A is twice the length of shape B. It's twice the height of shape B. Once I find the original scale factor or the scale factor of the linear dimensions, I can go ahead and write this here. So my perimeter and all my linear dimensions are in a scale factor of 2 to 1, or you can write it as 2 over 1 if you like the ratio as a fraction. We were given this scale factor. We calculated it by simplifying. That we said was 4 to 1, or 4 over 1. And again, this tells us that the original shape is twice the size of the new shape. My original surface area was 4 times the size of my new shape. And I'm asked to calculate the scale factor of the volume. To do that, I remember that volume scale factor is my original scale factor cubed. So I take my original scale factor, which was 2 over 1, and I'm going to cube this whole fraction, which is really just the same as 2 to the third power over 1 to the third power. 2 to the third power is 8. 1 times 1 times 1 is 1, or 8, which tells me that the volume of my original figure A is 8 times the volume of my new figure B. Write this as 8 to 1, or you can write it as 8 over 1. In both cases, you're correct. And guys, so that's how changes in scale factor can be amplified when we talk about area and volume. Thanks.